Welcome to May's Leetcode Challenge. Today's problem is prefix and suffix search. Design a special dictionary which has some words and allows you to search for the words in it by a prefix and a suffix. Now what they mean by that is they want us to implement a word filter class. Now the word filter class is going to initialize an object with the words in the dictionary, and we have a function here where we're going to pass in a prefix and suffix, and this returns the index of the word in the dictionary, so the order is going to matter, which has the prefix and the suffix. Now if there's more than one valid index, return the largest of them. If there's no such word in the dictionary, return a -1. So here we can see our dictionary has the word apple, and if we pass in the function prefix a and suffix e, that does exist, so we return 0. That's going to be the very first letter here. Now initially it seems pretty easy. You can probably try to solve this straightforward brute force, but that's gonna reach a time limit exception, and this problem is actually a lot more complicated than I expected, so we're gonna take it very nice and slow. Let's first read the hint here. For a word like test, consider hash test, t hash test, st hash test, blah blah blah. Then if we have a query like te and suffix t, how can we search for it for something that we insert here? Okay, so what this kind of tells me is, rather than checking to see like does this prefix exist in the first two positions and then the suffix position like that, what we can do pretty simply is create a string with both words with a hashtag in between them, and then if we do that, what we can do is take our suffix, put a hash in the middle and put the prefix afterwards, and just check to see if this exists inside that word. So say that if we had apple, we can say apple, hashtag apple, right? Now if we put the suffix and the prefix at the end like this, all we have to do is check to see if this value is inside here, and it is. It's right here, right? So that means this is true, and we can just return that. So let's just start with that approach and see if it works. What we're gonna have to do is, well, it's a little bit complicated because I already know the answer, but essentially we could have repeating words here. That's going to give us a time limit exception, and as well as that, there could be multiple answers, right? So there's two big gotchas we got to think about. So to take care of the repeating words, what I'm first going to do is create a dictionary, and I will move through all the words and store the index number as the value in our dictionary. So what I'll do is say for index word in enumerate words, we are going to add to our temp the word and update it with the index number. And this guarantees to us that if there's repeating words, we're going to get the maximum index number. Now what I'll do is initialize the words object or words list here, and we are going to say for key value in temp.items, I'm going to store the word but also the index number. Okay, and that's going to be important. Say store the key, which is the word, and the value as the index number. Okay, and luckily all these items here are going to be in order, so we don't need to worry about weird things happening here. Now we have these words, so what we'll do is write our function now. So first thing I'm going to do is write that prefix plus suffix, or rather suffix plus prefix, but in the middle I'm going to add that hash character. Now all we need to do is check for well, we have the index numbers inside here already, so we can say for the word and index number in self.words, if ps is in word, then we can return the index. Otherwise, if we get through this entire thing, we have to return -1. But keep note, it is possible that we have multiple words that have both the prefix and suffix. So we want to return the largest one, right? So to do that, I'm just going to reverse this guy. And that's going to guarantee us that we'll find the largest index number. So let's first see if this works. And that did not work. Always nice when that happens. Let's see. Words. Word, PS in Word, then return index. What did I do wrong here? Okay, well, let's see. Oh, yeah, of course. I forgot to add the hash in here. We'll have to add it up here, plus K. Okay, so that should work. Let's see. All right, so it looks like it's working. Let's go ahead and submit it. And it looks like it's about to hit a time limit exception, but that it does get accepted. Now this does get accepted, but it's barely passing. And that's surprising because the time complexity should be, let's say the number of words is going to be n, and the length of the words is going to be k, let's say. Then this should be n times k, but because of this, if PS in Word is going to be k again, it'll be n times k squared. But it's still kind of slow, so like, could we do better than this? Now the other approach that they try to tell you to do is, why don't you use a tree? Now that was actually my first thought when I saw this question, but I abandoned that because I wasn't sure how we would use a tree if we have, to search for a prefix and suffix in the middle. That would mean, like, do we need to build two trees or what? Like, I couldn't get it. But then I realized, oh, okay, I see. Like, what we can do is, we'll still have a tree structure, but we'll do this instead. We'll have this hash, and we'll do it for every single possible prefix going in front. So we'll add all these as like separate trees inside of there, or separate tree nodes inside of these in our tree structure. But the key thing here is we also need to update. We'll have to have the value of the index number inside of this tree somehow. So, all right, let's go try solving that way. It's going to take a while, but first what we'll do is initialize a tree node, or create a tree node class, and all this has is just two things. It'll have the children, which is going to be a dictionary of tree nodes, and we also in this tree node are going to store the index number. First I'm going to just have a -1, but each time we update this tree node here, we're going to add that index number here. Now, this might sound kind of confusing right now, but it'll start to make sense as I code this out. So now we have our class tree. What we'll do is initialize all there'll be here is what? The root. And the root is going to be a tree node, and that would be it. Now for the two other functions we need to have one for inserting, and we can just insert the word, but we also need to pass in the index number here. And luckily I have the index number that we can store inside of each tree node. Also need to have one for search. Let's call it find. And to make it easy, I'll say prefix, suffix, but before we do that, let's think about how we would add it to this tree. Okay, so for this tree, what I would do is take this word, and we're gonna iterate down our tree, starting at the root, and if we have this character as one of its children, then we're gonna just continue down that tree path, but update the index number. Okay, we'll be updating that index number at each tree path. And the reason that's okay is only the very last tree node position, like letter, matters. That's going to be what the index number actually is for this word. So first, what we'll do is initialize root, or take our self root, and I think I need to update this index number here with our index. Now for each character inside of word, what do I do? Well, if we'll take our root and children. So if C not in root children, well then we're going to add it. Okay, root children. take our C, and this is going to be a brand new tree node. Okay, next we are going to update our root to go to root.children C, and we should update the index number of this root to be whatever the index. And that should be it. We'll just continue down until we're done with the word, and the very last tree node will have indexed, which is the one that's the one that matters. Right now we have to do our find. So the first thing I'll do is create my long word here. I'll call it PS. It's going to be suffix plus hash plus prefix. Now we still have to start with the root, self.root, and for C in PS, if C not in root.children, well then this word doesn't exist, so we can return -1, or I should say rather this prefix suffix doesn't exist. Otherwise, we'll continue here with root going to be going to root.children C, and at the very end we'll return the root.index. And that should be our tree structure here. Okay. Now the key thing is, remember, we are going to be storing every prefix suffix combination with that hash in the middle inside of our tree. So that's kind of the main bulk of our algorithm here. Okay, so let's first initialize our tree. Now I'm going to, let's see, for index, right, sorry, is that right? If for index word and enumerate words, and let's see, this part might get a little tricky. First I am going to get the length of the word, I think. Length of the word. And what I'll do is create that temp. Well, I say word plus hash plus word. Take our self.t and insert. Well, I have to do it n times here for I in range of n. I'm going to self-insert this temp from the I onwards. And this guarantees that I'm going to get every combination. And just to make sure, I'll print this out here. Let's see, it's doing what I'm hoping it does. Oop, okay. Oh, right. Okay, pass in the index number. Okay, so here it is. Like, we're inserting this as a word into the tree, and this as a word into the tree. So this kind of guarantees that we have all the possible suffix prefix in here, right? Yeah, so that makes sense. And I think that's it. All we have to do now is return this function, and that would simply be returning, take our self.t and find prefix suffix. Right, so let's make sure this works here. Looks like it's working. Ah, there we go, accepted. So great. So technically this is supposed to be faster, but it's really not that much faster. It's slightly faster. Time complexity wise, it's the same. It's still n times k squared. And it's a lot more work, right? So is this worth it? I don't know. Now there's one more approach I'm going to go through, and I think this is the best one. What we'll do here is create two dictionaries instead. We're going to create two dictionaries for the prefix and suffix, and what we'll do is store the value as a set. And for every prefix and suffix that we can calculate for our words, we're going to make a set of all the index numbers in here. Okay, and at the very end, because we have all the possible prefix, suffix, index numbers, what we'll do is just get those two sets and find the overlap. We'll find the overlap between them and return the maximum index number that we can find that has an overlap with this prefix and suffix. So let's see what I mean. First, we'll create prefix of default dict and make that a set. Same with here. Suffix is going to equal default dict and a set. Okay, so now we're going to have the set. Great. Now what we need to do, see, one of the tricky things about this is now we have to worry about those repeating words and stuff. So what I'm going to do is have a set first and make sure that we don't store any repeating index numbers that we don't care about, especially if there's like a ton of them. So what I'll do is say n is length of words. We're going to move backwards. We'll say for I in range of n minus 1, minus 1, minus 1. We'll say if words I in scene, then we'll just skip it. Okay. Otherwise, let's add this word into the scene. All right. So now the tricky part. Let's first do it like this because it's going to get a little tricky. Okay, so the first thing I want to do is get the length here. I guess I'll call that k. K equals the length of w. And we need to store every possible prefix and suffix as well as the index number, right? Okay, so what I'll do then is say for the prefix, we're going to get w in the prefix. How will I do this? Well, I guess we have to do it for every k in range of k. Stuff.pw. That's going to be prefix, so it's up to k. All right, and I actually think we need to have a +1 here. But I'll double check on that. Say w, this would be from k onwards. And what we'll do is add the index number that we have right here. So let me make sure that I'm doing this right. I don't want to mess anything up, so let's just see. Okay. Okay, so I think that's working. Do store in a blank, but I don't know if that matters. I don't think that really matters. So we'll just keep that there. All right, so now we have everything that we need. All we need to do now, we're going to get the index number. Well, I can't do it. I guess I'll call it I. So we'll say, let's see, I self.p, find the prefix, and j equals self.s, find the suffix. Now the overlap. Okay, now these two are sets, right? And what we'll try and do is find the overlap between these two. So all we have to do then is say I and j, and we just return the max of this. Now of course there might not be anything here, so well, if that's the case, if not overlap, return -1. Otherwise, we turn the max of overlap here. Okay, so let me make sure this works. Okay, it looks like it's working. And accepted. So this is, I think, the optimal answer. Time complexity wise, it's still n times k, but it's this part that I'm not completely sure about. It's not quite k, this overlap part here. It might be. It might still be n times k squared, but it's just for whatever reason this part's a lot faster. In fact, this might be O1. I'm not positive about that though. Yeah. So this was a long one. I mean, it's kind of annoying that they started us off with a pretty difficult problem. Like, it's pretty straightforward to understand, but these solutions are pretty, like, not simple, you know, pretty complicated. So hopefully one of those solutions stuck out to you and you like those. I personally like this one, so I'm gonna stick with this, and hope that helps. Yeah, apologies for a long video. Thanks for watching my channel, and remember, do not trust me, I know nothing.